Today we're going to be talking about negative feedback amplifiers finally. And this is actually our first instance to where our op-amp circuit is actually going to behave like an amplifier as long as we design things correctly. Okay. So what we're going to do is we are going to analyze a circuit, and we're going to quantify some parameters for our circuit as a whole. And then we are going to revisit some topics from our very first lecture where we talked about what an ideal amplifier does, and then see if we can kind of relate these two things to develop some rules for analyzing negative feedback circuits in an easier way. So this way is legitimately the difficult way that I'm going to show you first, and then we're going to circle back around once we make some observations about things. So I am just going to have a simple amplifier circuit like we might have seen way back in circuits 1, and we are going to analyze this using the practical op-amp model. I'm going to have a feedback resistance here, which I'm going to call R2, connecting my inverting input terminal and my output terminal together. So we have negative feedback. This is going to be my output voltage. I am going to choose to ground my non-inverting input terminal. I'm going to have some resistor R1 like so. And then this is where my input voltage is going to be applied. So this is literally a circuit straight out of circuits 1 that we've looked at before. Let's say, for the sake of argument, that our practical op-amp has the following parameters. We have an open loop voltage gain of 10 to the 5 volts per volt, so 100,000. We have an input resistance of Rn is equal to 1 mega ohm. And we have an output resistance of R out is equal to 100 ohms. Let's say that our resistor value R1 has a value of 5 kilo ohms. Our resistor value R2 has a value of 10 kilo ohms. And our input signal Vn is simply 1 volt. We are going to find a number of quantities here. So I'm going to go ahead and define what they are. So I want us to first find the output voltage of our system. Then I want us to find the closed loop voltage gain. So it's going to be AVCL. And we're going to define that as simply the output voltage we determine from part A divided by the input voltage that we apply. So this is our closed loop gain for the system because we have a closed feedback path, right? It's going to be very, very different from our open loop gain of just the amplifier by itself. Okay. Then I want us to determine our closed loop input resistance, which I'm going to denote with this lowercase Rn to differentiate it from the uppercase Rn, right? So this uppercase Rn is the input resistance of the op-amp itself. This closed loop input resistance is the input resistance of the entire circuit, of the entire system. We're going to wind up figuring that out by taking the ratio of our input voltage to the current leaving the positive polarity terminal of our input voltage. So I'm going to go ahead here and call this particular current IN so that we can define Rn as the ratio of Vn divided by IN. We're also going to find the closed loop output resistance. This is going to be the same thing as the Thevenin equivalent resistance seen looking into the output terminals of the op amp. And then lastly, and actually we're going to wind up solving for this much earlier than lastly, I also want us to find out what value our differential voltage gain has. Or not our differential voltage gain, our differential voltage VD. Okay. All right, so the first thing that I'm going to do is I'm going to redraw this circuit using the practical op amp model. I'm going to choose to put my inverting input terminal on top because it's just going to make the feedback easier to draw. But our differential voltage VD is still going to be defined with the positive polarity associated with the non-inverting input voltage terminal, and the negative polarity terminal of VD is going to be associated with the inverting input terminal. So this is going to be very slightly different than what we've been doing. So this guy right here is going to be V minus. Here's my input resistance of 1 mega ohm. This guy right here is going to be V plus. And our differential voltage is now going to have the positive polarity terminal on bottom. And again, I'm just choosing to flip that resistor over effectively just to make the feedback easier to draw here in a moment. Over on this side, we have our open loop voltage gain, which is 10 to the 5 times our differential voltage VD. Here we have our output resistance of 100 ohms. And so this is our practical op amp model. And now we need to make all of our other connections, right? So our non-inverting input terminal was tied directly to ground. So I'm just going to put a short circuit here. Between our inverting input terminal and ground, we see that 5 kilo ohm resistor in series with our 1 volt input voltage. Just for the sake of argument, I think I drew it in blue earlier. I'm going to label this as IN since we'll wind up using that in a little bit. Now I'm going to put my feedback resistor in, and so I have negative feedback, so I'm connecting my inverting input terminal and my output terminal by that resistor R2, which I believe has a value of 10 kilo ohms. And my goal is to determine this voltage V out. So this is the circuit that we're analyzing to find V out, and then we're going to use this results of this to figure out some of those other quantities. So before we start our analysis, does anyone with how I've redrawn this circuit or any questions about how I've set things up here? Should be fairly straightforward, just doing the exact same thing that I've been doing for the last several class meetings. All right, so in order to solve this circuit for V out, I'm going to wind up applying Kirchhoff's current law at the inverting input terminal and at the output terminal of our system. So at the inverting input terminal, I'm going to be adding these currents together. So this guy, and this guy. And then the output terminal, I'm going to be adding this current and this current together. And I'm going to have to solve that system. So for KCL at the non-inverting input node, that's going to look like V minus minus 1 volt divided by 5 kiloohms plus V minus divided by 1 mega ohm plus V minus minus V out over 10 kiloohms is equal to 0. And KCL at my output node is going to give me V out minus V minus over 10 kiloohms plus V out minus 10 to the 5 VD divided by 100 ohms. Before we throw this into a calculator or anything, right? One too many unknown quantities, right? We have 2 equations and 3 unknowns. So V minus is an unknown, V out is an unknown, and VD is an unknown. But we should be able to look at our circuit diagram and very easily determine what VD is. So what is VD? Negative V minus. All right. So I'm going to replace this VD with a V minus. I'm going to change that sign from negative to positive, and now I have a 2-equation, 2 unknown system. That plus sign looks shitty. So solving this system simultaneously, what we're going to find is that our voltage V minus comes out to be positive 20.199 microvolts. And our voltage V out comes out to be negative 1.999392 volts. Keeping track of a whole bunch of decimal places here for reasons that you'll see in a moment. Okay. So with these 2 pieces of information, I can pretty easily solve for part A. Well, actually, I can't easily solve for part A. I just solved for part A, right? So we can say definitively that V out is negative 1.9999392 volts. Part B, our closed loop voltage gain, is going to be that negative 1.9999939, 392 volts divided by 1 volt comes out to be negative 1.9999392 volts per volt. For part E, we know that our differential voltage VD is just negative V minus, so that's going to come out to be negative 20.199 microvolts. So we've got 3 things from the jump. Before we move on to our system input resistance and system output resistance, yes. Microvolts. So 10 to the minus 6 volts. Very, very small. Any other questions? So our differential voltage here is a very, very small voltage, much smaller than what we've been seeing with our open loop systems and our positive feedback, where we were getting like several volts and all that kind of stuff. This is actually one of the characteristics of negative feedback, and we'll find it a little bit more. But whenever we have a differential system like this, our differential voltage is going to wind up being very, very small, almost 0. In an ideal case, actually, our differential voltage would be 0. And we'll see why that is here in just a couple of minutes. Let's look at our input resistance here. Okay. So our input resistance, lowercase r, which this is part C, is defined to be our input voltage divided by our input current. How are we going to quantify our input current in terms of things that we already know? So 1 volt minus V minus divided by 5 kiloohms. Okay. So Vn was just 1 volt. Now we're going to have 1 volt minus 20.199 microvolts divided by 5 kiloohms. And so this is going to come out to be 5,000.100997 ohms, or approximately 5 kilowatts. So for this particular configuration, where we are applying our input voltage through this resistor, the input resistance really just looks like this resistor. If instead we had applied our input voltage here, it would look something like this resistance. Okay. So for this particular configuration, it's going to be defined by this resistance, and for a configuration where we apply our voltage here and we ground here, it's going to look more like this one, and I'm going to have you guys show that in one of your homework problems. For our output resistance, that's going to be a little bit harder. Okay. So what I'm essentially asking us to find is the Thevenin equivalent resistance seen looking in to this output terminal. Okay. Now, there are a couple we could go about this. We could turn off this voltage source right here and apply a test source and find that resistance directly. Or we could find the Thevenin voltage across these terminals and the Norton current flowing through a short, if we shorted these terminals, and take the ratio of those two things. Which way do you guys want to do this? Take into note that we technically have already figured out what our Thevenin voltage is. So if we just find the short circuit current, that's the only piece of information we're missing. Okay. So I'm going to modify this thing right here. So this is our Norton current. How is that going to change our KCL relationships? Yeah, because now V out is just 0. Right? V out is literally tied directly to ground. So this V out voltage as a node is literally just 0. So what we would see is we would just have KCL at this node here to find V minus. That's our only unknown voltage in our system. And then we are just going to add this current and this current together to get I Norton. Does that make sense? So with this voltage being a known, the voltage at this node being a known quantity, we're only going to need to apply KCL here. The results of this KCL can be used to define this current, and then KCL at this node tells us that this current flowing in plus this current flowing in is the same as the Norton current flowing out. Okay. So we're going to have part D, V minus minus 1 volt divided by 5 kilo ohms plus V minus over 1 mega ohm plus V minus over 10 kilo ohms is equal to 0. We can solve this and find that our new V minus with our output short circuited comes out to be 445 volts. And our Norton current is then going to be V minus divided by, 10 kilo ohms plus 10 to the 5 times negative V minus divided by 100 ohms. And substituting in our value, we wind up getting negative 664.45176 amps. Now, I want to make a quick note here. If we were to actually short out the output terminals of our op amp, there is literally no way in hell we would ever measure this amount of current flowing through our op amp. It would fry it. Okay. So this is a mathematical exercise and not something that you could properly do this way. Realistically, we would set up a multimeter or something like that and just look into the dead network kind of thing to figure out what was going on. All right. So our lowercase r output voltage is then our Thevenin voltage, which is the exact same thing as our open circuited output voltage we already found, divided by our Norton current, or negative 1.9999, what was it up here? 392 divided by negative 664.45176 amps comes out to be positive 3.0085 milliohms. All right, so we've done some math here. Now, like I said earlier, we're going to revisit something that we talked about a couple of days ago. What it means for us to have an ideal amplifier. So on our first real lecture in this class, I drew a circuit similar to this. There we go, there's V out. Here is our load resistance. And this is the voltage drop across our load. And I believe I said something to the effect of, in an ideal case, our load voltage VL would be our signal voltage, V signal, multiplied by the gain of our system. Right? So the whole purpose of the amplifier is to make the voltage drop across our load look like a scaled version of the voltage that we're applying across the whole thing. So now we're going to figure out what actually makes that happen. Okay. So the first thing that we are going to look at is how to make Vn be identical to V sig. Okay. So how do we make the voltage that's applied across the input terminals of our amplifier, which is this part right here, be identical to the voltage that we're applying when we have this practical voltage source representation thing here? So what value must Rn have to make Vn equal V sig? Rn. So if Rn was exactly equal to Rs, I believe Vn would be 1/2 of V sig, which is not what I want. What kind of circuit is this? The voltage divider. Okay. So we know that for a voltage divider, in this case, Vn is going to be equal to V sig times Rn over Rs plus Rn, and we want this to be equal to V sig. How's that going to work? We can't change Rs. Yeah, if Rn is infinitely large, then we get this relationship. So for an ideal amplifier, our input resistance will be infinitely large. We're starting off from a place where it's on the mega ohm size, so we're almost there already, effectively. Okay. Now, we can see that our load voltage, VL, is going to be equal to AVOL, or yeah, let's call it AVOL for now. Really just A, but whatever. Times Vn. And then we're going to apply voltage division here and say that we're going to have RL over R out plus RL. And this needs to be equal to AVOL times Vn. So effectively, on the output side, we're going to figure out what value of R out makes this voltage equal to this voltage. So what value of R out causes that to happen? 0. Okay. So R out is equal to 0. And then the last assumption that we're going to make for ideal amplifiers is that our closed loop voltage gain must also be infinitely large. I can't really explain why this needs to work this way in the context of this class, but we'll talk about it significantly more in your later classes. So you'll just have to bear with me on that. Okay. So let's see what happens if we analyze our previous circuit under these constraints. So I'm going to start with my practical op-amp model. So here's V minus. And then I have my infinitely large input resistance. Here's V plus. This is my differential voltage, VD. Over here, I have infinity times VD. Over here, I have 0 ohms for my output resistance. Here's ground. This is shorted. This is 5K, 1 volt. $10K. Here's the V out that we're trying to solve for. So by inspection, we can see that our output voltage here, V out, is going to be equal to infinity times VD, right? Because if this resistance is 0 ohms, then it doesn't matter what current or anything like that is flowing through it, the voltage drop across it is always going to be 0. So by inspection, V out is equal to infinity, our voltage gain, times our differential voltage, VD. We could rearrange that to find that VD is just V out divided by infinity, or 0 volts. So in the case of an ideal amplifier circuit, our differential voltage will always be 0 volts. This is our voltage constraint relationship. And what this means is that if VD is always 0 volts, the voltage seen at our non-inverting input terminal must be equal to the voltage seen at our inverting input terminal, which was exactly one of the criteria that we used to analyze negative feedback op-amp circuits way back in circuits 1. So we know where this comes from now. We're just not making an assumption about things. Okay. So if VD is equal to 0, now we're going to apply Kirchhoff's current law at this node. And we know that since our input resistance here is infinity, that current is 0 amp, which actually is our current constraint for ideal op-amps, right? If this input resistance is infinitely large, then we can very easily see that no current can flow into or out of the input terminals of our op-amp, which was our second rule for analyzing ideal op-amps. Okay. So from here, we wind up getting KCL at V minus as V minus over 1 ohm, excuse me, V minus minus 1 volt divided by 5 kilo ohms is equal to, sorry, screwing this up, plus V minus minus V out over 10 kilo ohms is equal to 0. Since VD has to be equal to V out, and since V plus is equal to 0, this term right here goes to 0 volts. This term right here goes to 0 volts. And we wind up getting V out equal to negative 10 kiloohms over 5 kiloohms times our 1 volt input voltage is negative 2 volts. So let me ask you guys a question. How much error did we introduce by using an ideal op-amp here? Practically nothing, right? So we went through all of the work with the actual parameters in there. So Rn was 1 mega ohm, R out was 100 ohms, the open loop voltage gain was 10 to the 5, and we got an output voltage of negative 1.9999392 volts. Here, we threw away all of those values and just used idealized values, and we get negative 2 volts. So our error is well under 1%. So whenever we deal with negative feedback op-amp circuits, specifically where our open loop voltage gain is large, really anything over 1,000 will be good enough. Our input resistance is large, really anything over 10,000 kiloohms is good enough. And our output resistance is small, really anything less than a couple of hundred ohms, it's going to work like an ideal op-amp with a margin of error of probably less than 2%. So for all intents and purposes, dealing with a negative feedback amplifier means that we can just use the ideal op-amp rules and we really won't introduce all that much error into our calculations. So from here on out, other than the homework problems where I'm explicitly forcing you to use the practical op-amp model, we'll never do it again. It's a pain in the ass and it doesn't give us anything we can't get in a much easier way. Okay. Isaiah.
Say what you said again when we crossed out V5.
Sure. So we have here that our differential voltage VD is equal to 0. And so from that, we know that whatever voltage we have at the non-inverting input terminal must be equal to the voltage that we have at the inverting input terminal. Well, if you look at our diagram, the voltage that we have at our non-inverting input terminal is ground or 0. Okay. So, and I just want to be really, really clear about this. We're never going to redraw this thing either, right? So we could go back to a circuits 1, look at this circuit. Minus, plus, here's VCC minus, VCC plus. $10 kiloohms. V out, ground, 5 kiloohms, 1 volt, and we can just analyze it using this, right? So using my current constraint, I know that this current has to be 0 and this current has to be 0. I can see by inspection that this voltage is 0 volts, which means this voltage is 0 volts. Applying Kirchhoff's current law at this node, we get 0 minus 1 volt divided by 5 kiloohms plus 0 minus V out divided by 10 kiloohms is equal to 0. Solving for V out, we get negative 10K over 5K times 1 volt is negative 2 volts. The exact same result without having to redraw anything or go through any of that tomfoolery. Yes.
So to clarify, whenever we're given this scenario of ideal, it's always going to be V out equals negative R2 over R1.
For this particular configuration, which is what's known as a inverting amplifier, yes. And we are going to talk about those configurations again that I talked about in circuits 1 in our next class meeting. So we're gonna go over all of the commonly used negative feedback topologies on Monday. Yes, Toby.
So whenever we threw the practical up-in model, too far out, is that always possible?
Not necessarily. The reason why I say that is because an op amp is an active device. So that doesn't necessarily guarantee that we're going to have a positive resistance. The best example that I can give you guys of something that has a negative resistance is actually the ballast that's used in fluorescent lighting. For whatever reason, which I haven't dug into the physics of it, if you apply a positive voltage, you wind up getting a negative current. So all the negative resistance really means is that as the voltage increases, the current increases, but it's just flowing in the opposite direction you would expect. Nothing really wrong about that. It's just only happens when we have active devices that's even a possibility. Yes, Katie.
What is little Rn?
So little Rn is the input resistance of our system, not the input resistance of the op amp itself. Little R out is the output resistance of the system, not the output resistance of the op amp itself. So in your homework, I'm going to ask you guys to go through these steps and all of that kind of stuff with another situation like this, where our input signal is applied at the inverting input. At the inverting input signal or through a resistor network. I'm also going to have you do one where we apply an input voltage here, and you'll see that the output resistance is effectively always going to be something incredibly small because it needs to be as close to zero as possible to make sense. We'll see that, like, realistically, what we have here is this R1 in series with an open circuit. And so that's why we only see R1 by itself as the input resistance. When we're looking in through this guy, we're just going to see a huge resistance. Technically, it's going to have a value because we have a finite input resistance that we're looking in, but it's going to be astronomical. I don't want to get too far ahead. Like, I'm talking like 3 classes later in electronic circuits too. We're going to explore those relationships in a whole lot of detail. Yes, Isaiah.
Little R out.
So little R out is the system output resistance, and little R in is the system input resistance. Capital R out and capital R in are just for the amplifier itself without all of the biasing stuff connected.